So this is joint work with a lot of people who contributed over years, I would say. So I will go through a brief motivation, give some mathematical background. I hope you don't get scared by the many equations. I think it's interesting to figure them out a little bit. Talk a few minutes about implementation in OpenModelica, and then some concluding remarks. So the motivation is something that has been haunting me for a while, since when I started using Modelica in 2002 to build the power plant models. There's plenty of good stuff with equation-based object-oriented modeling and simulation. High-level modeling, declarative equations, self-documenting, causal. You can reverse causality, inheritance, model reuse, model solver separation. You write the equations, it's beautiful. Nice, shining objects. But you click simulate, and you get this. Depending on which application area you're in, this may be more or less frequent. If you're doing thermofluid modeling and you're not using thermofluid stream library, this happens all the time and has haunted me since the very beginning. So yeah, the fear is shiny, but it cracks and it reveals interiors which are really, really ugly. And then what? So, well, the tool tells you something. If you can read that, the color is not really great, not my fault. Well, yeah, this is OpenModelica, so it could actually be my fault, but never mind. Proper start values for some of the following iterations, variables might help. And then there's a very long list of iterations variables, all the way up to 62. So the tool is telling me, please give me better start values. Wow. So I'm quoting the Beatles here. Could you please help me? And the answer is now, yes, we can help you with this method. So let's see a little bit of mathematical background, how you actually do that. This is actually joint work between myself and Bernhard. This took some time. We started thinking about this in 2017, and eventually this was first submitted in 2019 and published in 2021. And then we managed to implement it this year. So it's been a long story for a number of reasons, but now it's done. So let me give you some notation. I think you're all familiar with Newton-Raphson's method. So we have to solve an initialization problem, which is algebraic. So it's f of x equals 0, where x are both states, algebraic variables, and possibly unknown parameters. It's important that we split the unknown variables into two subsets. W is the set of nonlinear variables, is the variables that are actually influencing the Jacobian, whereas Z are linear variables which do not influence the Jacobian. And we also split the residuals in nonlinear residuals and linear residuals. And this distinction is such that f of this vector can be split into a nonlinear function that also, by linear I really mean linear, not affine. So this nonlinear function also includes constant non-zero terms, and then you have a linear term which depends on the Jacobian with respect to Z. So this is the well-known Newton iteration. You start with an initial guess x0, and then you solve repeatedly these linear systems until hopefully x converges to the solution. Hope you're familiar with that. You don't have to spend too much time. So let me give you a few theorems. I don't love theorems, but in this case, it's really important. This is very well known. So if the Jacobian is non-singular at the solution, and f of x is Lipschitz continuous in a neighborhood of the solution, if you're close enough, this sequence will converge to the solution, and it will do so in a superlinear way. So basically, at each iteration, you get several more decimal digits. That's, of course, if you recompute the Jacobian all the time. Maybe you don't do it, but that's another story. This is very well known. I mean, it's the basics of the theory of Newton-Raphson's. This is also pretty well known. If equation is linear or actually affine, then basically it's a linear system. So one iteration of Newton gives you straight to the solution. That's very well known. This is almost trivial, but I couldn't find this theorem published anywhere, so we published it for the first time in this paper. It turns out that if you have these unknowns which are in part nonlinear and in part linear, it can be very easily shown that the values of the iterations at each step from the first one to the next one does not depend on the initial guess of the linear variables. You can put whatever value you want as an initial guess for the linear variables, and after one step, you always get to the same point. That is, of course, if you're using undamped Newton. If you use damped Newton, it's a little bit different. But in principle, this is interesting. So this, of course, has an important consequence. Never bother initializing initial guesses for the linear variables because it's not worth it. And then there's also another interesting theorem that we've proven. This is also easy. Not only it doesn't matter what initial guesses you give to the linear variables, but also the linear residuals, the residuals of the linear equations, will converge to zero immediately after the first iteration, no matter what. And they will always be zero throughout all the iterations. It's the nonlinear residuals that hopefully will converge and potentially could not converge and give you a headache. Again, that's if you're using the basic undamped Newton method. So there's a very interesting consequence of these two theorems. Consequence one, only nonlinear variable start values and only nonlinear equations matter. Don't bother about start attributes for the linear variable. Can be set trivially to zero. This is really important. I'm doing some work in the modeling of electrical power systems, big ones like national or continental grids. And in that case, like more than 90% of the equations are linear. And only a few variables are involved in nonlinear loops, nonlinear equations. So there's no point giving initial variables initial start values to all of them, only to the nonlinear ones. Now, here is the main question. Yeah, unfortunately, the question is covered by the thing. Sorry about that. The question is, how do we understand if we are close to convergence? Okay, you remember the first theorem. If you start close enough, you quickly get to the solution. And of course, there are some cases where you get nowhere. So how do we understand that? Our first idea around 2017 was to say, okay, let's compare the residual that we get with the initial guess with the residual after one iteration. Okay, if after one iteration the residual has shrank a lot, then it means we're probably close and it will shrink even more at the next iteration, right? Wrong, because as I said, we can actually set trivial initial guesses for the linear equation. So the linear residuals at x0 could actually be very large. It doesn't matter. You recall the theorem, after one iteration, they will get to zero. Okay, so looking at the value of the initial residual doesn't mean anything. We have to remove the effect of this linear part. So we have to define this nonlinear residual, which is the residual plus this term. And what this term does is basically to get rid of the effect of these large linear residuals, which go to zero anyway, as I showed you. Okay, this is the really important thing. So the criterion is if the residual after one iteration is much less than the nonlinear residual with the initial guesses, then there's counterexamples, but in most cases it means we're actually close to convergence. Okay, so we have to turn this criterion into something that can be expressed in some tangible way. How much time do I have? So here is a tailored expansion of each component of the residuals. This is the ith component at the first iteration, and you expand it around the initial guess. So there's basically a first order term, the Jacobian, and this is what the Newton-Raphson method will use to try to converge. Then you have a second order term with the Hessian, and then you have higher order nonlinear terms. I mean, if you have an exponential, there's infinitely many. So we can do an interesting, smart point here. We can define the order of magnitude of this part, the high order nonlinear residual, as a fraction of the norm of the nonlinear residual. Okay, and we do it for each equation. So this alpha I tells me what is the residual of these high orders compared to the total amount of error that I get with the first at the starting point. This is for every equation, and then we take the maximum of that. Then this is even worse. Never worry about that. This is basically the square of the deltas after one iteration, and this is the Hessian of the function residuals. If you define this thing, then you can prove this theorem if the sum of all of these things is less than some beta for every equation, J. And if you pick this alpha to be the maximum dose alpha, you can prove that f of x1 will have a norm which is less than alpha plus beta times the initial residual. I probably lost you at this time. Don't worry. This is the important theorem. What is actually, I just wanted to show you the mathematics behind it. You can look at it up in the paper. What does this mean? This has a very nice interpretation. Basically, if all the alpha i's, remember the alpha i's were defined, there's probably some problem here. If all these alpha i's are small, and if all the gamma I, j, k's are small, then these alpha and beta will be small numbers. Okay, so bottom line, if these numbers are all small, this will be small, and it means we're close to convergence. That's what this means. This is all rigorous. It's theorems that can be proven. Then we take a heuristic step. And the heuristic step is, if we don't get convergence, and there are some of these coefficients which are not small, well, maybe they are the culprits. That's the main idea. Because if they were all small, then it would converge with very high likelihood. So this is a little bit involved, but how you use it is actually very easy. You just need to compute these values, and you can have your Modelica tool do that. That's no big deal. Yeah, you need Hessians, but if you have Jacobians, you can have numerical Hessians. They don't need to be precise. You compute these indicators, and if you have large gammas, this gamma is ijk. So I is the index of the equation, and j and k are two variable indices. Okay, so if one large gamma iej exists, then this will point to initial guesses j and k, which are probably troublesome. And they will create trouble because of equation I. Whereas if you have a large alpha I, it points to a problematic nonlinear equation I because of high order nonlinear terms which are screwing up. This is very easy to interpret. It's also interesting to notice that this gamma ij, as you see this clearly, takes second order information into account. So what is really important is to take into account the curvature of f of x. And it's a combination of how much the solution is changing from the initial guess to the first iteration, but it's weighted with the curvature. And that's exactly what we were looking for. So that was one idea. Then Bernhard came up with another idea, which complements that nicely. We can go through that in a couple of minutes. The first theorem that we saw, which is classic, tells us that if the initial guess is close enough to the solution, x1 after one iteration will converge superlinearly. So it will be practically at the solution, which means if you change the initial guess, x1 will always be the same. So there's basically very little sensitivity. So we can actually compute the sensitivity after the first iteration with respect to the initial guess. This is some matrix sigma. And as I said, due to this theorem, if you're very close to convergence, this sigma will actually be zero. It's as if the function is locally almost linear. So it doesn't matter where you start from. So again, the heuristic argument is, well, maybe if the Newton-Raphson algorithm does not converge, then the culprits are likely related to the large diagonal values, sigmas, of this matrix. And this would point to some variables whose initial value is probably potentially problematic. Okay? Well, this matrix sigma can be computed by means of the Hessians here. You build this matrix, and then you build the sigma. So as you can see, it combines the second order information here, but also the Jacobian, first order information. Everything is packaged. That's basically it. So what we learned now is that in case of convergence failure, we can do the following steps. We compute one straight Newton step, no damping, no anything. We compute all of these indicators. We can rank them because we said the larger ones will probably point to something that creates trouble. So we just rank them. And then we can interpret this in the following way. Variables with potentially problematic start values are found in equations with large alpha i's, are pointed by j and k indices in these gamma ijk indices, and are pointed by I indices of large sigma ii. Whereas equations with large alphas and gammas may be possibly be improved, for example, by using homotopy. The problem with homotopy is you can, if you have a model with 100 equations, you could apply homotopy to all of them, and it would be a lot of work. But maybe it's just one equation which is creating trouble, and you only need to apply homotopy to that. Yeah, I'm almost done. So this method can actually point you to the equations which are worth considering for homotopy. This is good for the modeler rather than for the user. There's a caveat here. For technical reasons, you need equations and residuals to be well scaled for the method to work well. Otherwise, if you're computing this residual and you have one residual which is watts in a power plant at 300 megawatts, this is 10 to the 8, and another residual is 10 to the minus 4. If you don't scale them, this norm basically doesn't mean anything. That's just the technical remark. So that's the theory. We started the implementation, as I said, in 2021 with help from Karim and Andreas Heumann. Then the development started for many reasons. It was eventually resumed last year and finalized this year. So it's available in OpenModelica since version 1.25. It's been tested successfully in the examples that are shown in the paper that I mentioned. As I said, there's still a missing feature, the proper scaling of variables and residuals. This is ongoing work by Linus Langenkamp, which is probably here somewhere. It takes some time because this will require some refactoring of the code, so we want to do it properly, but it should be available like in December with the next release. So very quickly, I'll show you just one example. These are the equations of nonlinear electrical network. I could have added a drawing of it. There's one diode. Here we are saying that we want a certain total power consumption with a total current and total voltage. And then we have some Kirchhoff equations, and then we have some resistors. So there's a large number of linear equations, a mildly nonlinear equation, and a very strongly nonlinear equation. Okay. There's a known analytic solution, so you know exactly what the solution is. This is how OpenModelica breaks it down. So you see there are 13 iterations variables. In this case, we switched off tearing, and we have all of these residuals which correspond to these equations. What we did was we take the analytic solution and we tweak it by 10%. Every initial value is changed by 10%. Okay. You remember proper start values of the following iterations variables. OpenModelica tells me, look, there's 13 start attributes. Please fix them. And it's 13, and it could be like hundreds. But now, if you use our algorithms, it can tell us which ones. And that is interesting. If we rank those results that you will see here by variable, we rank the maximum values of gamma and sigma. Here, it clearly points out, I actually have special effects here, that VD is the culprit. VD is giving like a huge index. Then you have this current, which is involved in this equation here, but it's not such a big deal. We don't care. So you just need to fix VD. And the equation which is involved in the nonlinearity is the diode equation. So the method tells us exactly what we were expecting. So in fact, it turns out that if you fix the initial guess of VD, you can achieve convergence and you don't worry about all the other parts. So I'm done. Nonlinear iterations failures are a big problem. You need to identify which start values need to be improved. You may also need to identify strongly nonlinear equations to improve them with homotopy. And we have a method to do that. Thank you.